Sanne from the foundation, and I hope that everybody can hear and see me. And well, together with my colleague Christine, we will moderate the talk of Joshua. Please write your questions in the chat on the right-hand side. Joshua will answer them after his presentation. Okay? So first of all, I would like to present Joshua. So Dr. Joshua Philip Barham from the UK graduated from University College London and was awarded his industry-based PhD from the University of Strathclyde in 2017, after working primarily in GlaxoSmithKline on novel sustainable technologies in organic synthesis of medicinal compounds. After 3 years of postdoctoral research in Japan exploring continuous flow chemistry, he launched his independent research group at the University of Regensburg, supported by a Sofia Kovalevskaya Award in December 2019. His research team focuses on photoelectrochemically powered organic synthesis and continuous flow chemistry. In his spare time, Dr. Barham is a pianist and a keen hiker. He has climbed the highest mountains of the UK and Japan 3 times, and he is waiting for his opportunity to climb Zugspitze. So Joshua, thank you very much for being here today. And I would ask you now to start your talk with your presentation.
Okay, thank you very much, Suzanne, for the kind introduction. So I'm relatively new to the Humboldt family, having launched my group slap bang in the middle of the pandemic last year. And before I start, I'd just like to first express my gratitude to the organizers for the kind invitation to share some of our research group science, which is supported by Sofia Kovalevskaya Award. So today, I'd like to talk about how electrifying organic photocatalysis is a new frontier in light-powered organic synthesis. So AK Barham is an organic chemistry research group working within the themes of synthesis, catalysis, and sustainability. And we are particularly interested in emerging synthetic technologies and taming high-energy intermediates in synthesis. So our mascot here, the curious bear, is thinking about a number of synthetic technology platforms to achieve these goals. But for today's talk, I'm going to focus on photoelectrochemistry, which is our main research effort. Chemical synthesis by visible light is the fundamental process for biological photosynthesis on Earth. Carbon dioxide and water, like most organic molecules, do not actually absorb visible light, however, which is among the most available in the solar distribution. So to utilize visible light, nature's solution is chlorophyll, a colored pigment which acts as one catalyst in a complex photosystem. And some of you may recognize this photograph taken in the early 1900s. This shows an Italian chemist called Giacomo Camacan, whose vision was to mimic nature for artificial chemical synthesis. Since that time, researchers have stripped away the complexity of nature's photosystems into defined single molecule photocatalysts, like this ruthenium metal complex, which can be leveraged in artificial photosynthesis of organic molecules. Not only are the reaction conditions mild and using sustainable energy, they provide unconventional intermediates and new modes of reactivity that are really changing the way that synthetic chemists make small molecules. And this field, called visible light photoredox catalysis, really erupted in the turn of the 21st century and is now one of the brightest topics in organic chemistry. So how this works is we have a photocatalyst, which has to be colored, so this green sphere. And when this absorbs a photon, one of the electrons in the higher energy molecular orbital of this catalyst is going to be promoted to a higher energy unoccupied molecular orbital. Now, we're going to consider the energy of the highest energy visible photons, which are blue in color, and we can quantify how much energy is provided by the photon in terms of volts or electron volts. And this tells us about how much power the excited state is going to have to oxidize or to reduce a target substrate molecule of interest. So upon absorbing light, the photoexcited catalyst then undergoes an ultra-fast deactivation process. Even if we have enough photon energy to excite the catalyst to an even higher energy excited state, there is a rule called Cash's rule, which states that photochemistry always occurs from the lowest lying excited state. And because this photophysical deactivation is typically faster than diffusion and faster than photochemistry. Moreover, the spin of this electron can actually flip in the excited state to give a lower energy and longer lived excited state, which is this, for example, light blue sphere, that can undergo diffusion and then can find the substrate molecule. And when these two electrons are unpaired like this, the electron in the lowest unoccupied molecular orbital can serve as a reductant, and there's a hole in the highest occupied molecular orbital that can serve as an oxidant, hence photoredox. What happens then is when this catalyst finds the substrate, it can activate it, either by donating or receiving an electron into one of these orbitals. The activated substrate then undergoes downstream chemistry to give our desired products, and we'll see some examples of target substrate and product molecules later in the talk. This deactivated catalyst, the brown sphere, then needs to either give or receive an electron to regenerate the catalyst. And to do this, we need a sacrificial molecule of chemical oxidant or reductant, this molecule X. And its byproduct Y may interfere with this downstream chemistry here, and it also requires separation from the desired products. So not only is this wasteful from an atom economy perspective, it can also lead to issues of separation, and also these oxidants and reductants can sometimes be unsafe. But there's a bigger problem here, and that's the photophysical deactivation step. So we're losing typically about 20 to 40% of the input visible photon energy. And what this does is it limits the scope of molecules that we can oxidize or reduce in the first place. So we don't have enough energy to form or to cleave strong bonds like carbon-carbon, carbon-nitrogen, or carbon-oxygen that are of key interest to organic chemists in synthesis. How does Mother Nature solve this energy problem? Well, she can make strong carbon-carbon bonds. She makes glucose, which is photosynthesized from carbon dioxide and water. So how can she activate CO2? Well, the solution is actually the accumulation of visible photon energies. So in the complex system of photosynthesis, which I'm not going to go through, there are 2 photons of red light that are needed per electron transferred from water to CO2. So in total, there are 8 photons per CO2 molecule that is fixed. And this accumulation of photon energies is a phenomenon that researchers have really largely struggled to replicate in photoredox catalysis. So visible light photocatalysis needs a hand. Elsewhere, the accumulation and transformation of electrical energy is a fundamental part of human civilization and of our daily lives. So we considered that we could use electricity, or should I say electrochemistry, to activate a catalyst, say this light gray sphere, by removing or providing an electron to give this green sphere here. And this builds up a base layer of energy, say 1 volt. The electroactivated catalyst is typically colored, so the green sphere, it can absorb visible light photons. So therefore, a minor advantage of this approach already is we do not depend on a photoactive ground state. We can use a range of colorless precursors that are transformed into the colored catalyst in the reaction. And this greatly expands the possibilities of catalyst architectures. Then this electroexcited catalyst can absorb visible light. And the excited photocatalyst will react with our substrate in oxidation or reduction in the same way as we saw before. And downstream chemistry gives the products. So as you can see, another minor benefit compared to the previous approach is we no longer need these sacrificial chemical oxidants or reductants. But the key advantage, I would say, is that by combining the electrical and the photonic energies, the excited photocatalyst can now reach new frontiers, much higher than the parent concept of photocatalysis for oxidation and reduction, and it can enable more challenging target substrates to be engaged. What about the photophysical deactivation? Well, my philosophy to science is simple. If someone tells you there's a rule, break it. It's the only way to move things forward. So what if I told you that we found a way to break Cash's rule? And what I'm going to try to convince you in this talk is that a unique feature of this chemistry is that it occurs by a mechanism that is faster than the timescale of diffusion. So we can sidestep this photophysical deactivation, and we can harness the full potential of the photon's energy. One of the beauties of electrochemistry in organic synthesis is that we, the users, can directly control the energy that we apply to the reaction by simply turning a dial. However, the direct activation of substrates of interest typically requires an applied potential that is not only higher but constantly applied than the substrate. Electrodes don't tend to discriminate so well between molecules, so this can oftentimes lead to decomposition. Moreover, it isn't really an option for very challenging oxidations or reductions because we start to oxidize or reduce the solvent. However, this electroactivated photocatalyst offsets the applied potential energy by using the visible light, so it allows milder potentials for more selective reactions and engagement of tougher substrates. Okay, so what can we actually do with EPRC? Well, we can start to access super-oxidations and reductions of molecules that are impossible or inefficient to activate by photocatalysis or electrochemistry alone. And what this scale is really showing here is a roadmap of reactivity in oxidations and reductions. So don't worry too much about these labels. These are just the names of common catalysts or the abbreviations. But this purple bar basically represents the accessible realm of photocatalysis, with typical photoredox catalysts labeled in purple. We can't go beyond 2.5 volts on either side since this is the limit of the visible photon's energy. The light brown bar, on the other hand, shows the accessible realm of electrochemistry on its own. And there are issues of decomposition, as I mentioned, once you go plus or minus 3 volts on either side, because this is the organic solvent window. But using EPRC, we can break through these boundaries and the accessible realms of the previous technologies, and we can engage molecules beyond 2.5 volts on either side. We can even engage molecules whose innate potentials cannot be measured, at least by cyclic voltammetry, and we'll see this a little bit later. So now I'm going to share some of our group's progress in the area where we've developed some systems for both super-oxidations and for super-reductions. So our group recently reported triaryl amines as electroactivatable photocatalysts, since we can tap into the rich characterization history of their neutral and their electroactivated forms that derive from the ubiquity of these materials as whole transport materials in photovoltaics and also in organic LEDs. These triaryl amines can be prepared in high yields in a single step from relatively inexpensive commercial materials, and we can easily vary the substituents on the peripheral rings in order to tune the electrochemical or the photophysical properties of the catalyst, how we want them. We can also get so when we got the X-ray crystal structure of this particular catalyst with these para-cyano groups, I thought to myself, hang on a minute, where have I seen this structure before? Well, when I was a young lad in high school, I participated in the military cadets, and I learned to fly a fixed-wing aircraft before I got my driving license, actually. So British pilots learned to fly in something called the Grob G115, which is a tri-bladed turbo-propeller aircraft. And who'd have known that 12 years later, I would be piloting a molecular propeller that's made in Germany in a blue sky research project on electroactivated photocatalysis. So when we do our reactions, we use a cell like this, where the anode and the cathode compartments are divided by a porous frit. The unactivated catalyst, the gray sphere, is in the left chamber, and together with a carbon foam anode, this oxidizes the catalyst. The cathode can be a cheap copper plate or a platinum wire, and as you see, when we apply 1.4 volts across the cell, the electroactivated catalyst forms, which is green in color. We can also get the X-ray structure of this, and again, it is this similar propeller-type structure. Then we can apply the photon energy to the electroactivated catalyst with purple LEDs. And this electroactivated photoexcited catalyst can oxidize very tough molecules like dichlorobenzene to make an intermediate called a radical cation. And this can be attacked by a partner called a nucleophile in order to form a strong carbon-nitrogen bond. So we wanted to explore how the scope of this was, and using one of our least powerful catalysts, this one here, without the cyano group, we can activate, as you can see, moderately difficult arenes to CN bond formation. So mesitylene, xylenes, bromobenzene, and toluene as well. And as you can see in the top left example, we did the control reactions without the light, without the potential, and without the catalyst, and none of them give the product, confirming the photoelectrochemistry. Now, the benefit of using the visible light to offset the otherwise high requisite potentials to this low 1.4 volts is that we can tolerate other oxidizable groups in these molecules. For example, this sensitive aldehyde function or this iodine atom. And these are known to undergo oxidation at higher cell potentials when you use only electrochemistry. Using a more powerful catalyst, this one with the cyano group, we can activate more difficult arenes like benzene, chlorobenzene, and even fluorobenzene to oxidation. The carboxylic acid here is very sensitive to oxidation in photoredox catalysis and in electrochemistry on their own, but it is tolerated by our method. And by using the most powerful catalyst with 2 cyano groups, we can activate very hard arenes such as dichlorobenzenes, fluorobenzene, even acetophenone. The trifluorobenzene and trifluorotoluene can also be activated, albeit in lower yields. These molecules, they lie way beyond the reach of the visible light photon energy alone, and they even lie beyond the solvent window of what is possible with electrochemistry. We now made some peculiar observations when we wanted to try and understand how this reaction works. So the first was that the reaction only works with purple LEDs, even though the electroactivated photocatalyst absorbs red light very efficiently, as you can see here. Red light would promote the catalyst to its first excited state, but the reaction doesn't work there. So the chemistry seems to break Cash's rule, meaning it takes place from a higher excited state and avoids the photophysical deactivation and diffusion. Now, the second peculiar observation is the order of reactivity doesn't always follow the ease of oxidation. So the 1,2 disubstituted arenes tend to oxidize more quickly than the 1,4. So this one is more efficient than the 1,4 xylene. And also here we can see that toluene was more efficient than bromobenzene, was more efficient than iodobenzene, even though the ease of oxidation is in the opposite direction. And iodobenzene doesn't actually react at all. So this was quite surprising to us. And the same pattern of behavior occurs also for a different catalyst using the dichlorobenzene, so that you can see the 1,2 is more efficient than the 1,4. So to investigate this further, we worked with Professor Jürgen Hauer at TU Munich, who helped us to measure the lifetime of our electroactivated photocatalysts. And as it turns out, they only live for a few picoseconds in the excited state. So that's shorter than the time frame for diffusion. So we figured that the mechanism must be a little bit more complex than we originally thought. There must be some kind of pre-assembly between the electroactivated photocatalyst and the substrate, so that they're already in close proximity and set up to react when they're photoexcited. And this would sidestep the typical need for diffusion in most photocatalytic reactions. So we found some evidence of pre-assemblies by spectroscopy, and we did some computational modeling to see what these might look like in reality. And as a very simple model with one substrate molecule bound to one blade of the propeller in the bottom left of the electroactivated photocatalyst, structures like this one converged. We also calculated which parts of the electroactivated photocatalyst molecule are involved when we excite them with red light or with purple light. And as you can see in the top right, the transition with red light is mostly localized around the core rings of the catalyst. Whereas with purple light, the transition is mostly localized around the peripheral rings of the catalyst. And that's exactly where the computation predicts that our substrates are binding to the catalyst. And what we find is that the formation of these pre-assemblies is energetically more favorable for the arene substrates that work in the reaction, like chlorobenzene and 1,2 disubstituted arenes, and are much less favorable for the ones that do not work, like 1,4 disubstituted arenes and iodobenzene. You can read more about this in the reference. So we drew this kind of carousel as a cover artwork for our published manuscript. And what you can see here is the 1,2-dichlorobenzene is allowed on to ride the carousel, whereas the 1,4 and the iodobenzene are blocked. Sorry, you're too tall. The ride is then powered by electricity, and the rider comes off dazzled by shining lights as his excited state to bind with his partner nucleophile. Okay, so that's superoxidations, but what about superreductions? Well, electroactivated photocatalysis can also be used here. For example, to reduce compounds that are beyond negative 2.5 volts, like chloroarenes, we typically need things like lithium or sodium metal in liquid ammonia at minus 30 degrees. And these are conditions that are highly hazardous, unsafe, and avoided by industry. If we use electrochemistry on its own, the problem is we get over-reduction and we simply replace the chlorine atom with hydrogen, which is not synthetically very useful. But by 2 recent reports by separate groups, they showed how electroactivating and photoexciting these catalysts shown on the right, called DCA and NPMI, could achieve superreductions of chloroarenes and allow their synthetically useful functionalizations with trapping partners. And inspired by these reports, we found that superreductions using this NPMI catalyst could also cleave strong aliphatic carbon-oxygen bonds. And depending on the nature of this neighboring substituent X, we can affect an olefination reaction or an overall deoxygenation reaction of aliphatic alcohols. The setup is similar to before, but this time we use blue light instead of purple light. We can use iron and zinc as very cheap cathode and anode materials, respectively. But what we found that was quite interesting was while the previously reported NPMI catalyst was generally ineffective in this chemistry, a modified one developed by us was generally effective. So how does this work? Well, the electroactivated catalyst, this guy here, gets photoexcited. It becomes a superreductant in the exciter state, and it reduces the activated alcohol, requiring around 1 to 2.6 volts. The activating group is this phosphonate shown here. The activated substrate then undergoes a CO bond cleavage to give this radical, and this can be further reduced and eliminate the chlorine to give an olefin. If there's no leaving group, no chlorine atom, just a hydrogen atom there, then we get overall deoxygenation. And we can use this method to make a bunch of olefins. Of course, there are other chemical routes to make olefins, but these typically require methods involving strong acids or strong bases. And our strategy doesn't require either of those, so we can tolerate base-sensitive groups like esters, and we can control the site of olefination, for example, terminal over internal olefination. And as you can see in the top left here, we did all of the control reactions without light, without potential, without catalyst, and none of them worked. Interestingly, the previously reported catalysts, DCA and NPMI, they didn't work. They were ineffective in this application. And you can see here the yields in red only worked for one substrate, but for all the other ones, it didn't work with this older catalyst. Whereas our modified catalyst delivered all the products in successfully. But what was even more intriguing than that, as opposed to previous reports that reduced chloroarenes, our chemistry actually tolerated chloroarenes. And even more sensitive bromoarenes didn't even react. Iodoarenes, which are the most easy to reduce substrates normally in photocatalysis, didn't even react at all. So the selectivity here is really profoundly different to any of the previous reports on reductive photocatalysis and is highly surprising given the superreductive conditions that we're using. But our strategy was actually applicable to some complex natural product molecules, and we applied it to these fragrance oils and liquid crystal materials in order to make monomers that could potentially be used in fragrant or liquid crystal polymers. We also demonstrated a couple of deoxygenation reactions, for example, to synthesize limonene, which is the scent of lemons. And if the neighboring chloro group of the substrate was moved one atom further away, it actually led to cyclization instead of olefination, and this confirmed a carbon anionic intermediate. So what's the difference, though, between the previous catalyst and our new modified one? Well, the graph on the left shows that they're electrochemically the same, whereas the graphs on the right show that their electroactivated forms absorb light at the same wavelength and the same intensity as one another. The only difference between these two catalysts that we could see is their shape, their molecular structure. Again, we found that this chemistry breaks Cash's rule. There's no reaction with red light, even though the catalysts absorb that light, reasonable efficient. So we thought again here, the pre-assembly may be the key, and the shape of the catalyst must influence this. So we thought that maybe the bulky isopropyl groups of the older catalyst might be hindering the pre-assembly. And so what we did is we varied the structure of the catalyst, making the ortho groups smaller each time to see what was the yield of the reaction. You can see making smaller each time and then gone. And what we found was, satisfyingly, that the yield actually increased across the series. We also calculated which parts of the electroactivated photocatalyst molecule are involved when we excite them with red or blue light. And as you can see in the bottom, the transition with red light is localized on the naphthalene part of the catalyst. So there's no change. However, the transition with blue light, which is required for our reactivity, shifts the transition from the naphthalene part to the aniline part of the catalyst. So we therefore hypothesized that this aniline part must be involved in the pre-assembly to bind the substrate and undergo this anti-Kasha photochemistry. We then did some computational modeling of this, and we found a number of favorable pre-assemblies. In all cases, the substrates converged in a kind of pincer orientation like this, where the substrate catches the catalyst aniline group. And the energetics of this pincer binding actually became less favorable as the bulk around the aniline got thicker. So it kind of reminded me of how in nature, scorpions that have thicker tails tend to have smaller, weaker pincers. So our catalyst may be more effective than the original MPMI because it forms a tighter pre-assembly with the substrate. And we did this study in collaboration with Professor Regina de Vivi-Riedler at LMU in Munich. So overall, this chemistry reminded me of a padlock and a key. You need the right key to turn the gears of the electroactivated photocatalysis in order to unlock the carbon-oxygen bond. Here is a picture of a Gothic key, and there can be no more appropriate analogy for chemistry that was developed in Regensburg than the city's emblem showing the two crossed keys of St. Peter. So with that, I'd like to thank my motivated and wonderfully international group of postdocs, PhDs, and master students for realizing this work, and my colleagues, Professors Koenig and Reiser, for supporting me on my journey thus far. Of course, photoelectrochemistry and pre-assembly in photocatalysis are very formidable challenges to our understanding, and they require great collaborations with spectroscopy and theory. So I'd like to thank also colleagues at LMU Munich and as well as Dr. Butera at CTEC in the Czech Republic. And I especially thank the Alexander von Humboldt Foundation for funding and the SynCap Master Program of the Elite Network of Bavaria for providing me with very talented master students, some of whom have started PhDs in my team. So with that, thank you all very much for your kind attention. And before I open the discussion to questions, I'd just like to show you a little video on how we do these reactions in the lab. So what you can see here is on the left-hand chamber of both sides, two different electroactivated photocatalysts. One is going to green and one is going to blue. These are both the triarylamine propeller type catalysts. So those are two examples, and I'm now going to show you another two examples. These are the paracyano catalyst and the unsubstituted catalyst here. You can see turning blue. And what we're going to do next is we're going to lower these cells into the cooling block on which the LEDs are mounted, so that we can keep the reactions at room temperature and we can irradiate them with high-powered purple light. So with that, I'd be happy to take your questions.
So thank you very much, Joshua, for this very interesting presentation. And there are, of course, several questions already in the chat, and I'm going to read them. So Dr. Soresa Abera Chaya, she says, it's a very informative talk. Thank you, Professor Joshua. Could you please comment how the activation process governs the efficiency? And could you explain the mechanisms of the activation process for the modified and not modified catalysts?
So I'm not sure exactly what they mean by the activation process, but there are two processes involved. So the first process is the electrochemical activation. So this is the one that forms the photocatalyst. So if we do not have this electrochemical activation, nothing happens when we shine light on the reaction. In terms of the efficiency, I would be more inclined to talk about the photochemical efficiency of the reaction. And this is something that we haven't quantified yet. So we need to measure something called the quantum yield. And we need to quantify, how many photons of light we put in the reaction versus how many product molecules we get out at the other end. And that's something that experimentally has been a little bit challenging for us to do so far, because it is quite difficult to set these reactions up in a way that we can measure these quantum yields. But we are working on this, and we're trying to develop a flow system to do this in a very thin path. And this would hopefully allow us to quantify these things a little bit more. I would also love to tell you more about the Faradaic efficiency of the reaction from an electrochemistry point of view. But the problem is that when we apply a constant potential across the reaction, we are measuring the current. And we can measure this current, but what happens is the moment that we apply the constant potential, the current drops to almost zero because we activate the catalyst. And from this point onwards, the current is below levels of detection. So we need to get more sophisticated galvanostat or potentiostatic equipment to look into these efficiencies a bit more. But if I want to talk about efficiency from an organic chemistry point of view, I'm going to talk about yields. And as you can see, the yields in our reactions are generally reasonably good. They're generally higher than the yields that you would get from using electrochemistry on its own.
So thank you, Joshua. So the next question is from Dr. Arti Tiwari, and he says, very entertaining and informative talk. For the superoxidant, PTCU was used, whereas for the super reductions, FAZN was employed. Do you suspect they play a role in the respective reactions?
Yeah, absolutely. So I just want to clarify. So for the superoxidant, we used platinum or copper as the cathode, but for the anode material, we always used carbon foam. And so when we think about using the right cathode material, we have to think about the hydrogen evolution reaction. In some of our reactions, we are adding a small amount of acetic acid or water. We need something to turn over the catalyst. So if we're oxidizing things at the anode, we need to reduce things at the cathode to provide those holes. And so we use acetic acid for this, and we tended to find that for the more challenging oxidations, we needed platinum because we were applying higher cell potentials. So instead of 1.4, we were sometimes applying as high as 1.8, and in those cases, we needed the platinum because it had a higher over potential. And so that, I hope that answers the first question. For the second part, iron and zinc. So we use the iron here as the cathode, and we use the zinc here as the anode. And what we did in these super reductions is we did not add a corresponding sacrificial reduction there. We simply sacrificed the zinc, right? So we used a sacrificial zinc cathode. So the zinc simply oxidizes, to zinc oxide during the reaction. And zinc is very cheap. We can buy electrode grade zinc from Amazon, eBay. We can use this in our reactions, and we just simply dispose of these. And we use the iron as the cathode for the same. Sorry, my mistake. We use the zinc as the anode. We use the iron as the cathode for the same reason. So iron is very cheap. The reaction does work with carbon foam also as a cathode, but we found that the carbon foam, especially that's been treated RVC at high temperature, it can be a little bit brittle. So when we're stirring the reactions over time, we can see some mechanical shearing of the electrode. So we thought that using an iron plate would be more robust. And what we'd like to do in the future is, rather than dispose of our electrodes, when we do this on a larger scale, we'd like to do this in a flow reactor and use a divided cell electrochemistry there. So instead of sacrificing our electrodes. So I hope that answers the question. You're absolutely right. The electrode material plays a key role in the respective reactions. And I think that's for a number of reasons. Some of I've already discussed, but one also is that in these reactions, we can be generating radical intermediates, especially carbon-centered radical intermediates. And those intermediates sometimes graft onto the electrode surface. So that may explain why some electrodes are more suitable than others. But the key benefit of using this EPRC is that because the reaction is a photochemical reaction, it takes place at the surface of the cell. So in the bulk, it doesn't take place necessarily at the electrode because the light doesn't penetrate in that far. And so that's how we get selectivity compared to direct electrolysis.
Okay. So thank you, Joshua. So the next question is from Professor Sayam. He says, nice lecture. I see that some aliphatic substrates were used for the super reductions. What kind of pre-assembly do you expect?
So I'll just go back to the slide I think that they're talking about here. So actually, in all of these cases, there was an aromatic group in the substrate. So this is a limitation, I would say, in this chemistry, that we need to have a phosphonate that comes from a benzylic alcohol. If we do not have this aromatic group, the chemistry doesn't work. And that could be to do with the precomplexation, as I suggested, but it could also be to do with the stability of the intermediates in the reaction. So we showed that we have a radical and an anion, and if you have a benzylic radical or anion, these will be more stable than an aliphatic one. Also, we have to consider that in all of these are all the products, of course. The substrates all have this phosphonate. So the phosphonate is this diphenyl phosphonate. So this also has two aromatic groups. And we think, based on the slide I showed you, we think that the substrate aromatic group and the phosphonate aromatic group are involved in this pincer. So we think both parts are essential. And we're trying to understand this interaction in a little bit more detail. And as you say, it would be really nice if we could also find these kind of dispersion interactions with aliphatic substrates. But so far, we haven't succeeded to engage substrates that don't have an aromatic position. So we're still working on that.
Okay, thank you. So the next point is from Dr. Hossein Goudasi, and he says, very amazing. Thank you for your wonderful presentation, Professor Barham.
Dankeschön.
I guess that everybody agrees here, so no question to answer here. And Professor Dr. Sayam says, do you know what the excited state lifetimes of the reduced NPMI?
Yeah, that's a very good question, and it's a very relevant question. So we showed obviously the lifetime for our triarylamine radical cations, but we didn't mention the lifetime of these catalysts. And indeed, this has been done in the literature before, not for this exact catalyst, but if you shift the alcohol group one position over, you have the 1,4 substituted NPMI, then it's known the lifetime of these is of the order of several dozen picoseconds. So these catalysts also live shorter than the timescale of diffusion. But this is something that we would like to measure in the future. And so to do this is a little bit more technically challenging than for the triarylamines, because those radical cations, they are bench stable. So we can make them chemically. They're beautiful purple or blue or green solids. We can keep them open to air for weeks and they're fine. But these radical anion catalysts are actually not very stable. So we have to prepare these if we want to do spectroscopy in the glove box. And to measure the lifetimes of these with transient spectroscopy, it will take a little bit of time to get the right technical setup for this. But we will in the future work with our collaborators at TU Munich to try and get some numbers on these things. But what I can tell you is there's literature on this. You can check in the preprint we have on ChemArchive. We're very pleased to announce that it will be accepted for publication in Angewandte Chemie. So you can check in the supporting information and the main text, the references for those lifetimes of similar compounds.
Okay, thank you. So Professor Yu says, beautiful talk. Is it easy to scale up the photoelectron synthesis in the lab?
So I can actually, just as a little bit of a teaser or shameless self-promotion, I can tell you that we've just submitted a review on this area. And one of the topics of the review that will be included is on scale-up, scalability up to at least gram scale, multi-gram scale. And so we're certainly not talking about kilos or tons or anything like manufacturing. But this is a new technology. It's only appeared in the last, I would say, couple of years, or should I say the renaissance of this has appeared in the last couple of years. There was a report back in the 1960s, but it didn't get much attention then. So this has only just appeared, and people are starting to work on better ways to do this. But I can tell you that there are several reports where people have done this, usually using a recirculated flow approach. So you have a batch electrochemical reactor, a round bottom flask with your two electrodes, and you pump the reaction mixture through a coil, which you irradiate with LEDs or lamps or whatever. And so far, most of the progress has been on this recirculated flow. And this works up to about 20 grams or so. But what I would say is that this applies to a slightly different type of photoelectrocatalysis. The one that I'm talking about, where you have these radical ions, this has not yet been scaled up. But there's another type where we simply use the already well-known photocatalysts that are used in photocatalysis on their own, and we recycle them with electrochemistry. And in that recycling approach, this has been demonstrated, on some gram scale. And so all I can say is watch this space. There'll be a review out on this, hopefully, in the coming months that you can read all about the scalability.
Okay, so thank you. And Dr. Godasi has two questions. Question one, do you think these materials can be used as photo initiators for bioprinting application? And question two, are they useful as dual color photo initiator or not?
Dual color. I assume what you mean by dual color photoinitiator is where you use more than one photon to access these radical ion catalysts and then excite them again. So there is a complementary concept, if you will, where what you do is you excite the neutral catalyst, not the radical anion, and it oxidizes a chemical reductant to become this radical anion, and then you photoexcite it again. And I assume that's what he's talking about. And that process in the literature is referred to as CONPET, so consecutive photoinduced electron transfer. Indeed, these catalysts can be used in this CONPET mechanism. So that's no problem. We can do this with, for example, triethylamine or Hunix base. We can access these radical ions, but the reason that we use electrochemistry is because we don't want to use these sacrificial organic reductants that interfere with the reaction. So that's why we chose to use the electrochemistry. The other reason that we choose to use the electrochemistry, which I think this reduction shows really nicely, is it changes the mechanism later in the chemistry. So if we were to use only the photochemistry, the CONPET, we get to this radical, but then that stays as the radical. So only by using the electrochemical method can you reduce that radical again to the anion. And so the electrochemistry actually allows you to change the downstream chemistry as well. So that's one of the reasons we're interested in it. And to answer your question, actually, with an example, we tried doing this reaction, this substrate that forms the 7-membered ring olefin. We tried doing this with CONPET, but it doesn't work. And we think that it doesn't work not because the CONPET doesn't work, but it doesn't work because that radical doesn't get reduced to the anion. And so, yes, you can use these catalysts in different chemistry, no problem. We like this photoelectrochemistry because we think it opens new opportunities for mechanism and also makes reactions a little bit more green on there. The other part of the question on photoinitiators for bioprinting applications. So I am not an expert in bioprinting, but I assume that this maybe requires an aqueous media and things like this. And so the answer is probably no, not yet, because we need to first develop catalysts that are more stable or soluble in aqueous media. These catalysts so far have all been studied in acetonitrile, but not in water, for example. And the other problem, I think, is if you would do this in water, is the hydrogen evolution reaction. So there's going to be a competition between reducing your catalyst and reducing your protons from water. But there may be a potential to do this if you choose the right catalyst. You could use potentially a potential that's lower than the HER, and maybe then you could use this for these kind of applications. So I would say just early days on this, and so far we've just seen the applications in organic synthesis. But I think, yeah, I'm hopeful about the opportunities for this in terms of applications and also things like polymerization, because you think about the chemistry, it's taking place in the bulk solution, not at the electrode. So you're not just going to reduce all your active intermediates.
Okay, thank you. So next question is from Dr. Yang. Thanks a lot for the nice talk. Can you explain again bicombing photo and electrochemistry? And this strategy is particularly useful for what kinds of reactions?
Okay, so as the first point, I'll try to explain this a little bit briefer this time. So there are three benefits to doing this. So the first benefit is if we consider the photochemistry on its own, we can get to about 3 volts here of redox potential because of the visible light photon. And by using the photoelectrochemistry, so that's the first disadvantage. The second disadvantage, as I mentioned, is we need this sacrificial chemical oxidant or reductant to turn over the photocatalyst, at least if we're doing oxidations or reductions in these reactions. If we then look at the photoelectrochemistry, because we use with this base layer of electrochemical energy, we can then get to much higher overall energies of the catalyst. So we can get up to about 4 volts or potentially 5 volts, depending on the system that we're using. And the other reason, or the other thing that I mentioned, the other kind of unique facet is this pre-assembly that seems to happen. And this means that we can avoid the photophysical deactivation that we always have in photocatalysis. We always have a deactivation to a long-lived excited state. But here in the photoelectrocatalysis, these catalysts are so short-lived that if they do not do the chemistry in a pre-assembly, it doesn't work. So if the chemistry works, it means that you can access these really high potentials. And we've shown 2 applications of where this works. As to what kind of applications we can do with this, I would say, for example, show you. So we can make the CN bond by oxidizing arenes like benzene or chlorobenzene. And we can oxidize, for example, very, very difficult arenes like dichlorobenzene, fluorobenzene, acetophenone. These cannot be oxidized by photocatalysis alone. And if they are oxidized by electrochemistry, you can be sure that you'll decompose a lot of your solvent and get very low yields on there, because the solvent is usually easier to oxidize than these molecules. So that's the key advantage of the photoelectrochemistry. It's the high power, and it's the pre-assembly, and it's also the green chemistry. So avoiding these sacrificial oxidants or reductants that you typically need in photocatalysis. And I think for the reductive side, we also showed one application. Yeah, so we made these olefins. Okay, that's okay. But we also showed some applications towards making potentially monomers for polymerization. And if you would think about making these from the Wittig reaction, which is another classic olefination, that usually involves a strong base like butyl lithium. And it's questionable how well the ester would tolerate the butyl lithium.
Okay, so thank you for your answer. One more question from Dr. Huang. Thank you for your beautiful lecture. Have you ever considered the role of solvents in photocatalysis, such as trying the reaction in alternative media?
Yes, we have. So when we do these reactions, we typically look at acetonitrile because this is a very common solvent. It's a dipolar aprotic solvent, so it's good for conductivity. We normally have to add some supporting electrolyte on there to make it more conductive. But we can also use, for example, dichloromethane, although that's less green. And we can use dimethylformamide, so an amide type solvent as well. We haven't yet looked into water, as I mentioned earlier. We first need to try developing a soluble catalyst for water. But you could also think about using things like ionic liquids, which are obviously highly conductive, and these days you can buy relatively cheap on there. We will look at, for example, in the future using carbonate, so like dimethyl carbonate. That would be a very green biodegradable solvent. What else have we tried? So sometimes we do notice that the solvent is key. So we cannot use, for example, if we're doing reductions, we cannot use dichloromethane because this is very easy to reduce. But we can use acetonitrile or DMF. And for oxidations, we can use all, I think acetonitrile or DCM both work fine. The reason we chose acetonitrile, as I say, is it's the least it's not so high boiling, so we can get rid of it after the reaction, and it's the least environmentally concerned compared to the others.
Okay, so are there any more questions? Please use the chat. So we have 9 more minutes left. I would just like to say at 4 o'clock, I will move everybody back to the lobby. So you may then take part in our brain dates, where you will be randomly connected to other participants for a couple of minutes. But this will happen at 4 o'clock. And there's one more question from Dr. Huang. How about deep eutectic solvents?
Yeah, so we haven't tried this yet, but I think this should work because these deep eutectic solvents, they typically consist of ions, and if the ion is a oxidizable anion, then we can probably develop a catalyst that's lower than that oxidation potential. So we could definitely think of doing that. We haven't looked into that yet, and that might just be due to concerns of removing the solvent after the reaction to get our products. But certainly for some of our reactions, we could do this, especially where we make the olefins. We could simply add something like pentane at the end of the reaction and extract the product out. So it's not something that we've tried yet, but it's definitely on the to-do list in terms of solvents. So I just want to kind of emphasize again that this is a relatively new field. So even before I started the group in December 2019, I think there was one report on this. And in the last 2 years, I would say there's now over 15 or 20 papers in JACS, Angewandte, these kind of level of journals. So this field is really exploding. And I think it's because people have started to hit the limitations of what they can do with photocatalysis and electrochemistry on their own. And they're starting to think about, what happens if we put these things together? And it makes total sense. We are using photoelectrochemistry for water splitting and things like that, for hydrogen generation. So why are we not using this for synthesis? We should be using this more for synthesis.
Okay. So any other questions? Yes, from Dr. Liang. One more question. Sometimes we use it as strong oxidant, sometimes as strong reductant. How to control the selectivity?
Yeah, so I guess I can flip back to the roadmap slide. So that's up to you. You're the user. You can choose the catalyst that you want to do oxidations or reductions. And so I wrote a review on this in 2020 where I showed this kind of roadmap, and this has exploded since. So I think on that review there was only 3 or 4 different examples of these electroactivated photocatalysts. So these are the ones in green. But now there's all of these examples you can see here, and you can pick your catalyst. If you want to do reductions, you can pick from any of these ones. If you want to do oxidation, you pick from one of these ones, and you simply apply the potential that you need to make that radical ion. So For example, if you want to do a reduction at -3 volts, you can take this DCA, so you can reduce this at -0.9, and then you can add the photon energy, and you get to this guy here, -3 volts. You want to do oxidation, you can start with one of our propeller type catalysts, these triarylamines. So you generate these at around 1 volt, 1.4 volts, then you add the photon energy, and you have these excited states here. So that's really up to you. You can control that reactivity by your choice of conditions. How you control the selectivity, so I think that's an inherent a property of this chemistry, that we generate our catalyst at the electrode, but our catalyst then goes into the bulk solution. And it has to be excited by the light. So it has to go to the surface of the reactor vessel, near to the LED, where it can see the light. So that means that when we do our oxidations or reductions, we're molecularly speaking, we're quite a distance away from the electrode. So that means we can form things like radicals without further reducing or further oxidizing those intermediates. And we see a very good example of this in reductions of chloroarenes. So with electrochemistry only, you just take out the chlorine and replace it with hydrogen. But with photoelectrochemistry, you can make the aryl radicals. And the aryl radicals are easier to reduce than the starting material. So if you did this with electrochemistry only, it goes to the electrode, it gets double reduced, and that's game over. So I think that's an inherent thing, but as I mentioned kind of towards the end of the talk, we really think that this pre-assembly that we mentioned here might be able to be used as a kind of selectivity control parameter, because the substrate wraps around the catalyst like this, and it's only this part of the molecule that gets reduced. So that's why we think we reduce the CO bond and not the chloroarenes in those molecules. So we think we can. We're really excited about this pre-assembly and what opportunities this kind of non-covalent interaction might have in the future.
So thank you very much. We have 3 minutes left. So yes, everybody's saying thank you very much and congratulations for the nice talk. So this was really amazing. Also on behalf of the Humboldt Foundation, thank you to everybody for listening and taking part. And well, please enjoy the rest of the of our annual ceremony. And I will send you back to the lobby, and you may take part in our brain date starting at 4 o'clock, where you will be randomly connected to other participants, and this is quite fun. So.
Can I just jump in there? So if anyone has any further questions, I can see there's one more in the chat, for example. Feel free to drop me an email. I'd be very happy to talk to you and answer your question by email. So that's absolutely fine. You can find my details on the University of Regensburg's homepage. Yeah,
and there is, I see it right now, Dr. Alberto, there is one more question.
And maybe I can answer this real quick. So So we are trying this right now, actually. So first row transition metal catalysts. Yeah, we would love to do this. These are very easy to modify with electrochemistry, and they're usually photoactive with the right ligands. We actually got some funding for this recently from the Daimler-Benz Foundation. So we will be working on this exact area of research, and look forward to sharing some with you in the future.
Okay. So thank you once again, and see you all at the brain dates, or in the chat, or somewhere else, and have fun. And thank you for joining in today.
Thank you, everyone.